right, well, good afternoon, everyone. It's 3:30, so we'll go ahead and get started. Welcome to today's joint EOL M-Cubed seminar. I'm Sarah Woods, and on behalf of EOL and M-Cubed, I'm pleased to introduce Ms. Michelle Storm. Ms. Storm achieved her Bachelor's of Science in Meteorology from Metropolitan State University in Denver with a minor in mathematics before heading to the University of Wisconsin for her Master's in Atmospheric Sciences. Ms. Storm is now pursuing her PhD in meteorology at the University of Oklahoma, focusing on coastal urban planetary boundary layer processes and interactions in Houston, Texas. During her research career, Ms. Storm also worked at the Atlantic Oceanographic and Meteorological Laboratory as a NOAA LaPenta intern, investigating the effects of tropical cyclones on upper ocean characteristics in the northern Atlantic. As part of the Research Experience for Undergraduates program, she also interned at the National Weather Center, studying the heterogeneous structure of the Great Plains nocturnal low-level jet and its possible influence on convective initiation. Ms. Storm's research interests encompass observational meteorology, boundary layer processes, mesoscale circulations, numerical weather prediction model analyses, convection initiation, and pre-convective environments. These interests have engaged her in 6 field campaigns, land, UAS, and ship-based, including Taurus, Tracer Cubic, Perils, and most recently, Lift, all of which you can ask her about during her ASP graduate visit with Bill Brown and Tammy Weckworth. She's here through March. On that note, please join me in welcoming Ms. Storm for her seminar titled Spatial Variability in the Diurnal Evolution of Planetary Boundary Layer Heights in a Coastal Urban Environment. Michelle?
Hello everybody, thank you all for coming today. This is a great turnout. I wasn't sure what it would look like with the snow, so thank you all for coming in person, and for those of you online, I appreciate it. And thank you to Sarah for that awesome introduction. My first slide was going to go through some of what I've done, but I can skip this now because she did a great job. So we'll just jump straight into the sciences. So the planetary boundary layer, or the PBL, is the dynamic interface between the Earth's surface and the atmosphere. This portion of the atmosphere is pivotal in driving meteorological processes that influence weather patterns, climate behavior, and pollutant dispersion. The PBL responds to surface forcings on the order of minutes to hours and exhibits a distinct diurnal cycle, an example of which you can see in this figure on the right-hand side. This figure depicts the numerous different pieces that make up the PBL, with your growing convective mixed layer during the day, the residual layer that takes place after the sun sets, and the nocturnal inversion near the surface that makes up the stable surface layer. Given that the PBL is directly influenced by the Earth's surface, the characteristics of the PBL vary quite a lot from location to location because of the heterogeneous nature of the Earth's surface. So one of the key parameters associated with boundary layer research is the PBL height, which is important in many forecasting applications, such as those for air quality, convection initiation, and numerical modeling parameterization development. This is an important parameter. However, it is difficult to define, and it's hard to observe, partially due to our limited observations through the depth of the PBL. The heterogeneous nature of the PBL, both temporally but also spatially, also adds to the difficulty in estimating planetary boundary layer heights. As such, we rely on observations of PBL characteristics like thermodynamic profiles, vertical velocity observations, and aerosol concentration measurements to estimate the PBL height. Several different instruments and methods are used for this estimation. A large portion of past PBL height-related research has relied on radiosonde observations for estimations, but a growing number of studies have begun utilizing space and ground-based profiling systems like ceilometers and lidars. These different instruments use a variety of different methods for determining the PBL height, whether that be the height of temperature or humidity gradients or the height of aerosol gradients. An example of different radiosonde-based methods is shown in the figure here on the right-hand side, with the left panel exhibiting a clear sky case and the right panel a more atmospherically complex case. If we look at the clear sky case, you can see that there's a lot less variability in the estimated PBL heights, but if you look at the more atmospherically complex case, these estimated heights can range over 1.5 kilometers in depth, which can have significant impacts on forecasting applications. For my project, we use a fuzzy logic method that combines multiple observation sources that I'll explain furthermore in just a moment. Now, we've already established that the boundary layer is a complicated place to understand because of limited observations and large amounts of variability. So why not add a little more complexity to the mix? Coastal urban environments experience unique and complex PBL processes due to the nature of the heterogeneous land surfaces across land and sea. And so we have interactions and PBL processes that include things like mesoscale coastal breezes, as well as urban heat island effects, an idealized example of which you can see here on the left-hand side. This particular figure shows the daytime progression of land and sea breezes as well as air pollutant transport. So in the early morning on the top, you see the land breeze can act to advect air pollution from over the city out over the sea, but as the daytime progresses and a sea breeze develops, that pollution can then be advected back over the city, and you can have areas of enhanced convergence along that sea breeze front that acts as a lifting mechanism for convection initiation. In addition to the coastal breezes, the land-atmosphere interactions are also affected by the heterogeneous nature of the land cover and surface roughness changes across the land and sea interface and region. These different land characteristics and processes lead to unique dynamics that can significantly influence weather pattern, the local weather, particularly air quality conditions. Coastal urban regions often experience unhealthy air quality levels, especially in port locations where there are increased pollutants from shipping and freight operations. An example of ozone exceedance days is shown in the figure here on the bottom right for the Houston area for a 23-year period. While there has been a decline in the number of 8-hour ozone exceedance days in this region, you still have over a month's worth of days reaching unhealthy levels, which means that this area is still being affected by unhealthy air quality despite that decline. So given that a large portion of the world's population lives within these coastal urban environments, it makes this area an important region in place to study and further our understanding of small-scale processes. Understanding the behavior of the atmosphere and how it interacts with the land can be important for a multitude of different applications in these environments, including things like water resource management, air quality forecasting, and sustainable urban development, which leads us to some of the work I'll be sharing with you today. So Houston, which is the 4th largest city by population in the United States, is a prime coastal urban environment to study, with it being home to a complex aerosol makeup, frequent summertime convection, and compounding small-scale meteorological processes. The city has a history of poor air quality, as we saw on the last slide, in part due to the numerous pollutant resources and sources ranging from oil refineries, shipping and transportation, and agricultural operations. Many numerical models also struggle to accurately simulate the planetary boundary layer in this region and the small-scale processes that take place, necessitating more research into these complex issues, which brings us to the coastal urban boundary layer interactions with convection, or cubic, campaign that took place in Houston from June 1st to September 25th of 2022. This project aims to investigate and understand the many complicated mesoscale circulations, processes, and interactions that take place throughout the area and how these processes modify the PBL. For Cubic, we deployed 3 mobile profiling units in a semilinear transect through Houston, which you can see in the map here on the left. Each site was chosen to sample differing PBL environments, with Clamps 1, the northern site, as our urban location, Spark as our rural location, and Clamps 2 as our coastal site. The shading on this map depicts the local climate zones, and while the Clamps 1 and Spark locations are within relatively similar zones, they are expected to be distinct in the air masses that are being sampled because Clamps 1 is downwind of Houston, while Spark is downwind of the more vegetated land cover. So each profiling system collected continuous high temporal resolution thermodynamic and kinematic data through the depth of the PBL, with some minor data gaps due to instrument issues and brief significant weather events. Anybody who works with observations can probably understand what that is like. So with each of the profiling systems, we have a Doppler wind lidar, atmospheric emitted radiance interferometer, surface meteorological station, and then the Clamps trailers also included a microwave radiometer. An example of the data that was collected during this campaign is seen from our Clamps 1 site in the top right panel. This particular case experienced a sea breeze that went over the Clamps 1 site, and you can see both an increase in moisture after that sea breeze front passes over the site, as well as decreased vertical velocity measurements. This photo down on the bottom is just an example of what these trailers look like. This is Clamps 2, and it was located at the University of Houston's Coastal Center. With this nearly 4-month-long campaign in deployment, we were able to capture some really interesting features, including things like nocturnal low-level jets, land breeze circulations, and some really interesting aerosol layers, especially in the overnight period. Obviously, with Houston being a coastal location, the sea breeze is a common feature during the summertime months, and we were able to observe a total of 50 cases with our platforms, including a suspected estimated number of 16 cases in which it appears that the sea breeze forced convection to initiate. So overall, we have a pretty rich data set with a lot of different things that can be investigated and looked into, but for this talk, I'm going to get back to the PBL heights. So as I mentioned earlier, I've applied a fuzzy logic method and algorithm that uses the kinematic and thermodynamic data from our Clamps and Spark platforms. Fuzzy logic methods have been used in the atmospheric science field for many years and have recently been applied to PBL height estimations. The algorithm used here applies a combination of Haar wavelet transforms and membership functions in a 2-step approach to come up with our finalized estimates of PBL height. The first step involves the use of measurements of mixing, so things like vertical velocity variance or the height of a temperature inversion, to determine the first generation aggregate. Then a check is applied to ensure that the estimated height is connected to the surface by finding the lowest height at which that aggregate value falls below 0.5. The second generation aggregates are found using indicators that mixing has occurred. So things like SNR ratios and a constant wind speeds within a layer. The same aggregate threshold is applied to the second generation aggregates, and then the estimated heights are smoothed via a triangle mean to result in the finalized height estimations and associated uncertainties. This algorithm was created by Dr. Smith and Carlin and expands on the work of Bonin et al. 2018, in which only LiDAR measurements were used for height estimations. The addition of the thermodynamic data can help the accuracy of this algorithm during transition periods when temperature inversions have a greater impact on PBL heights. These thermodynamic data and the methods used within this algorithm helps to also ensure that the PBL height is staying connected to the surface, which is a key distinction between PBL height and mixed layer depth. So the code is openly available, and you can use it. You can apply it to different observation sources. You can find it at the link here. It's part on NOAA OAR's GitHub page. And if you're more curious about all the inner details of it, this workflow diagram on the right-hand side depicts all the different steps that go into these height estimations, and you can also find that on the GitHub page as well. So once the PBL height algorithm was applied to each site for the duration of the campaign, we can start moving into the analysis and really get an idea of the PBL height characteristics throughout the Houston area. Here we have the campaign averaged PBL heights for each of the 3 sites. Focusing in on the daytime boundary layer, we can see that there are some interesting differences between the sites, both in the timing of the maximum PBL depth and the differences in the depth themselves. At Clamps 2, which is, as a reminder, our coastal location, the maximum PBL height is reached at approximately 18 UTC at a height of about 1,100 meters, or and this occurred about 1 p.m. local time. However, if we look at Clamps 1, the maximum height isn't reached until almost 2 hours later, and it's at a depth of about 1,600 meters. This difference in peak timing could possibly be influenced by the sea breeze, which often impacts Clamps 2 and Spark, but doesn't always propagate far enough inland to reach the Clamps 1 site, or if it does, it reaches so close to the evening and sunset transition. So in addition to these timing differences in when our peak PBL heights occur, we also have a depth difference between the sites as well, with a difference of roughly 480 meters between the Clamps 1 and Clamps 2 sites, despite there only being about a 60-kilometer difference between those locations. So we can look at these averaged heights throughout the campaign, and it gives us a general sense of some spatial and temporal differences, but just how variable can these heights actually be? To look into the variability, I have here the averaged height plus and minus 1 standard deviation for each site, and this really provides a great visual for the variability that was seen throughout the campaign. Focusing in on our urban site first in the top left panel at Clamps 1, we can see that there's a decent amount of variability, particularly during that middle afternoon period and again in that overnight time period. Conversely, at Spark and Clamps 2, we have less variability, with our coastal site at Clamps 2 showing the least amount of variance. The PBL at Clamps 1 is also consistently deeper than Spark and Clamps 2, possibly indicating more vigorous mixing taking place at that site. With Clamps 1 being located within an urban setting, the environment is likely being affected by the urban heat island, which could also explain the generally deeper PBL depths that we see in that overnight period. So these initial campaign average results indicate some spatial and temporal differences, which naturally leads to our next question of what factors are actually contributing to these differences, both spatially and temporally. To begin investigating this, in the different aspects that may be responsible in the PBL height differences, we use self-organizing maps to categorize our synoptic regimes over the region. This is a machine learning technique in which data is provided and a pre-described number of nodes are given, which the algorithm then finds patterns in the data and produces results like what you see in the figure here on the left, in which the algorithm finds patterns and each node has a piece of data that has similar patterns within. For our SOMs, we use 21 years worth of summertime geopotential height reanalysis data from the ERA 5 archive. We chose the 700 hectopascal level to capture the near surface synoptic flow patterns, but with minimal effects from the Sierra Madres Mountains to the southwest of our domain. We applied a 2-stage sorting to our SOMs, with the first being an 8x8 set of nodes, and when we did this first set of sorting, it comprised of a node entirely of tropical cyclone days. So we eliminated those days because that's outside the scope of what we wanted to focus on. We verified them against satellite imagery before doing so, and then reran the process again for a 3x3 set of maps, which resulted in what you see here on the left, in which we have distinct flow patterns over the Houston area. The table here on the bottom right is just some quick statistics regarding the regimes throughout the region. Over the 21-year period, Houston experienced southerly winds about 69% of the time, which is only slightly lower than during the summertime cubic days, in which we had southerly winds 70% of the time. The second most common regime over the Houston area was a northwesterly wind flow, which occurred on 21% of days throughout the cubic campaign. So looking at the PBL height and how it varies across these different synoptic regimes, we can see that the heights show little variability at a specific site depending on the synoptic regime. SPARC is the only site that indicates a synoptic regime effect on the PBL heights, with the northwesterly regime leading to heights about 375 meters deeper than the other regimes. These deeper heights could indicate urban influences being advected over the SPARC site as it's downwind from the Houston metropolitan area. Since we don't see similar influences in the northwesterly regime at clamps 1 or clamps 2, I don't think that the purely continental air mass being advected over the sites is necessarily accounting for that difference. So our results indicate that the synoptic regime doesn't really account for the variability that we see in the PBL heights. So that means that local and smaller scale processes are driving the differences in the PBL height. Obviously, again, with Houston being a coastal location, the sea breeze is known to modify the PBL. However, how much it modifies different characteristics is not really well understood, especially in a spatial sense. So focusing in on the sea breeze and how it may be impacting the PBL, I have here two different cases from clamps 1. On the left side panel, you will see a case in which a sea breeze didn't develop. We can see your pretty classic convective boundary layer taking shape just before 14 UTC, a gradual building of the boundary layer before reaching a pretty steady height of about 1,600 meters for several hours, then the decay in those heights as the sunset approaches and the daytime heating is lessened. On the right is a sea breeze case, and there are some pretty clear differences both in the PBL height evolution throughout the day, but also the thermodynamic and kinematic structures at the time of the sea breeze passage. So if we zoom in to the sea breeze passage, we can see there's a clear decrease in PBL height as the cooler and more moist air mass passes over the site. There's also a decrease in the magnitude of vertical velocity, indicating less turbulent conditions behind that sea breeze front. This is just a single case example of how the sea breeze can modify the PBL, but how different are the PBL heights when we compare sea breeze versus non-sea breeze cases throughout the campaign as a whole. That's what we have here with our campaign averaged heights for the two different types of cases. The sea breeze cases are the solid lines, while the non-sea breeze cases are dashed lines. The sea breeze cases result in deeper heights at each of the three locations, with the greatest differences occurring at our urban and coastal locations. Interestingly, though, the timing at which we see the maximum PBL being reached doesn't vary all that much, which was a little surprising on my end of things. So one of the other things that we can kind of see in this is that there are differences in the PBL height decay when you start approaching sunset and that rate of the decay. So the next question is whether we can identify different PBL characteristics responsible for these PBL height differences. For the next couple of slides, I'll be showing time series plots where the x-axis is normalized by the time at which the maximum PBL height occurred. Now, this is not a perfect method by any means because there are numerous different things that can lead to when you reach your maximum PBL height, but given the results from the last slide where our timing between sea breeze and non-sea breeze cases are pretty close together, this is what I've gone with, at least for now. So this particular time series plot is a 6-hour time series of our 100 to 200 meter layer average potential temperatures. And this is, again, with sea breeze versus non-sea breeze cases. So sea breeze are the solid lines, while non-sea breeze cases are dashed. There is a noticeable difference between sea breeze and non-sea breeze cases with warmer temperatures on sea breeze days compared to non-sea breeze days. There's also a spread between the sites. Clamps 1 is generally warmer than the coastal location. Makes sense, it's in that urban setting. It's further removed from the coast. But you see that Spark and Clamps 1 on non-sea breeze days are pretty similar in terms of their low-level temperatures. So I also looked into the low-level winds, again, average over the 100 to 200 meter layer, and we can see that there are weaker winds on sea breeze days compared to non-sea breeze days. Unlike the low-level temperatures with our urban site, where our urban site exhibited the greatest differences in temperature, Clamps 2, our coastal location, has the biggest difference between sea breeze and non-sea breeze cases in terms of those low-level winds. Spark is still kind of in that middle ground between the two. So these thermodynamic and kinematic time series results help to show that warmer temperatures and weaker winds are more conducive to sea breeze development and are also consistent with deeper boundary layer heights. This is consistent with a lot of past sea breeze related research. In terms of the warmer temperatures, weaker winds tend to increase your number of sea breeze days. Given the deeper heights for the sea breeze days, I also wanted to investigate the vertical velocity variance profiles between the sea breeze and non-sea breeze cases to get an idea of the turbulent structure for each type of case and whether that plays a role in our deeper heights. So when we average over a 3-hour period with our vertical velocity variance profiles here, we can see that there are increased variance on sea breeze days compared to no sea breeze days, both at our Clamps 1 and Clamps 2 location, but we don't see that same signature at the Spark location. This increase of variance on sea breeze days is just another piece of the puzzle to understanding why our heights are deeper on sea breeze events. Past literature has shown that greater turbulence will lead to deeper boundary layers, and our findings throughout CUBIC are following that same principle. So we've explored some observations of the PBL in the Houston area, and found that there are some substantial differences spatially and temporally in PBL height, especially between sea breeze and non-sea breeze cases. We've been able to investigate and see corresponding trends in temperature and kinematic structures between those two types of cases, but these observations are still only 3-point locations in space, which really limits our ability to fully understand the spatial and temporal differences that we're seeing throughout the CUBIC campaign and the PBL and heights and modifications to the PBL. So there's great utility in using modeling simulations to further our understanding of the observations that we collect, but also in investigating different aspects of model configurations as well. So it's really a back and forth mutual benefit potential when you have observations and modeling simulations to be used together, especially in a campaign like CUBIC, where you have a longer duration data set and you can have an increased number of cases to compare modeling simulations to and with. So as a part of CUBIC, we worked with Dr. Gibbs at NSSL to run some case study simulations using NSSL's War-on Forecast System, or WoFs for short. This particular model ensemble was designed specifically for short-term 0 to 6 hour forecasts targeting high-impact weather like thunderstorms, hail, and lightning. So applying this framework to CUBIC is a little bit outside of the norm for what WoFs is typically used for, but it allows us to explore other potential utilities of WoFs. WoFs is a WRF-based high-resolution convection-allowing model ensemble that includes a rapid update assimilation cycle, data assimilation cycle at 15-minute intervals. Observations are assimilated from the multi-radar, multi-sensor radar reflectivity and radial velocity data, surface meteorological stations, and from GOES satellites. The initial and lateral boundary conditions are provided and generated by an experimental HER ensemble analysis, and the configuration is set up in a way that produces 6 unique physics combinations. We chose to run the WoFs simulations for 11 cubic cases in which the sea breeze appears to have forced convection to initiate in the Houston area. Our hope going into the modeling side of things with this project was that WoFs would be able to simulate the sea breeze and also capture the convection initiation that takes place along the sea breeze front, regardless of the fact that sometimes this sea breeze front is pretty weak compared to other mesoscale type systems. For today, I'll be sharing some of the initial modeling results from a case that took place on August 17th. Now, I will caveat this with the fact that I haven't had a lot of time to dive into this yet. I've really just now started to transition to looking into this, so this is a very initial look at one of these cases. So the August 17th case produced a sea breeze that was observed at each of our 3 sites, leading to discernible modifications to the thermodynamic and kinematic structures within the PBL, and it produced convection over the Houston-Galveston region along the sea breeze front. The radar animation in the top left, or top right panel is from the NexRad radar in Houston. And you can see that as the daytime progresses and the sea breeze front starts to propagate inland, you have some discrete cells starting to pop up along that sea breeze front. The time height plot here on the left-hand side is from our Clamps 2 coastal location, and this is showing our wind speed on the top and wind direction on the bottom. And this is just to help show what the sea breeze front looks like as it passed over the site. At this particular location, it passes over Clamps 2 at about 19 UTC. So looking into the WoF simulations, this animation is showing our surface temperature and wind barbs from 17 to 23 UTC. As the day progresses, you can see the temperature along the coast cooling as the sea breeze propagates inland, and the wind shift from a kind of sporadic, calm mishmash of directions to a more southerly flow with that sea breeze. This particular animation is from ensemble member 2, which you can see the PBL scheme and radiation schemes listed there, but it is representative of the other members in this ensemble. Every ensemble member was able to produce a sea breeze on this given case. Now, again, our hope going into this was to accurately simulate the sea breeze and the convection that took place during this event. While the sea breeze was captured by every ensemble member, the ensemble members were not uniform in their representation of the convective potential. These 4 ensemble members, which are just a few to show the differences, help to represent kind of the spread that we saw in terms of the simulated convection over the area. Some of the members produced little to no convection over Houston, while other members were overzealous. While this is interesting and definitely something I want to look more into, it's outside of the scope of what I'm currently looking at, so instead I'm going to focus more on the boundary layer characteristics and how they compare with our observations. So one of the greatest utilities and benefits of the profiling units that we deployed is our ability to capture continuous observations through the depth of the boundary layer, which is typically only possible twice a day if you're relying on radiosonde observations. So the plots shown here are the PBL profiles extending to about 2.5 kilometers above ground level. The observed profiles for each site are in the black dashed lines, while the solid lines are the ensemble members, and they are colored based off of the PBL scheme used for the ensemble member. One of the first things that probably catches your eye here is the fact that each of the simulated profiles are several degrees warmer than the observed profile from about 250 to 2,000 meters above ground level, with varying degrees of accuracy in that very close near surface layer. The other clear difference here is that the YSU ensemble members exhibit a 1 to 2 degree warmer surface temperature in near surface temperatures that's then carried throughout the profile to about 1,500 meters before coming back into better agreement with the other ensemble members. This is consistent with some past research looking into models sensitivity studies that have shown systematic warm biases with non-local mixing schemes that produce larger mixing and associated warming and drying. So looking forward, I really want to try to build a better understanding of the physical processes that take place. We're able to see with our observations some of these general trends on sea breeze days, for instance, but having a better idea of what is driving these physical processes would be awesome, and I hope to use the WoF simulations alongside our observations to help get at some of those more fundamental understandings. This is just a very quick look at the observed and estimated PBL heights on the left, and then the model PBL heights for that second ensemble member. This is just the parameter that's output by the model. So with that, some key takeaways from my project so far is that the PBL height varies spatially and temporally throughout Houston, regardless of the synoptic regime, and even in really small, relatively small spatial sense. Sea breezes can exhibit deeper PBL heights than non-sea breeze cases, and our WoFs ensemble, at least for this first case that I've looked at, was able to produce the sea breeze, but it did not always capture the convection along the sea breeze front. So some of my next steps moving forward is to look and try to quantify the impact of different PBL parameters on the PBL height. We saw some corresponding things between warmer temperatures and deeper heights, but having a better way to actually quantify these different parameters would be awesome, and that's what I'm working towards right now. Similar thing with the sea breeze. I would like to look specifically at sea breeze cases themselves to try to understand what the level of impacts are with the sea breeze on the PBL. And then I'd really like to do a more in-depth case study of this August 17th case using the WoF simulations and really look at the pre-convective environment, both with our observations and with the WoF's simulation output. There are always questions that still need to be answered. That's why we're all here. So these are just a few of them. I'll leave them up there for you. But thank you all. I'll take any questions. And also, this is my work from home coworker, AERI. I always have to introduce him in my talks.
Thanks, Michelle, for that very interesting talk. Quick comment for those of you online, we are still taking questions on Slido. The interface has changed slightly. If you look above your live video, there's an extra tab that's marked Slido. You can enter your questions in there. Do we have any questions from the room? You can use either microphone.
Thanks, Michelle. That's great. So, question for you about the transition in the evening and your technique to diagnose the boundary layer depth from the measurements shows that the boundary layer collapses to 50 meters or something. And you talked about the urban heat island keeping it relatively tall through the evening. So what is the mechanism that makes it collapse completely, or is that just an artifact of your algorithm?
So that is partially an artifact of the algorithm, but also the AERIs recycle at 0 UTC. So they shut down for a moment and then have to restart, and the algorithm is picking up on that right now. So one of the things that this algorithm does, and one of the outputs that you can write to your files, is your mechanical versus your buoyant PBL height estimations. And I don't have an example of it here, but when I look at that, our buoyant is going to 0 because we're recycling and missing out on a little bit of data right at that 0 UTC time.
Yeah, but you don't see that at Spark.
You don't see it at Spark, not as much. I don't know why yet. But when I look at the or it's clamps too that we're not seeing it as much.
Is that what it is?
Yeah. So I haven't figured out exactly why that is yet. Still trying to figure that out. But if you look at just the mechanical estimate and you neglect the buoyant estimate at that time period, you have a more gradual decay in those heights. So that little time period is something I'm still trying to tease out exactly what's happening there.
Thanks.
Great. Matt, did you have a question? And then we'll do online.
Sure. Can you go back to your slide where you showed the Smith and Carlin plot of PBL structure very early on? I think it was only.
Yeah.
So I look at this and I'm like, so what's the PBL height? Like, if you have all these different zones and boundaries, like where do you draw the PBL height in these plots?
Yeah, that's a great question. That is one of the joys of PBL height research is how exactly are you doing this? So in this particular plot, in the way that we are estimating the heights is we are combining a lot of different methods together. So we're looking for temperature inversions. We're looking at the vertical velocity variance, signal to noise. So in this particular example here, we have these different pieces outlined, but if I were to just draw it based off of what we have, in the way the algorithm that we use works is we would have this as like our nocturnal layer because this residual layer is no longer connected to the surface. So it's really trying to find that height at which we're still being affected by the surface forcings, if that makes sense. I don't know if I fully answered your question or not.
Okay, yeah, thanks.
Okay.
So we have a question online from Dave Turner. Great talk, Michelle. Quick question. The AMF also had an AERI, i.e. there were 4 of them in the domain, and it might be a better comparison with clamps 1 because of its fetch instead of the spark system. Is there a reason why you didn't use that instrument in the analyses?
I don't necessarily have a good reason why I haven't used that in the analyses yet. I need to look into the version of the thermodynamic retrieval that was used with that particular instrument to see if it's the same version as what we've used for ours. So our thermodynamics are, we apply a retrieval algorithm called TROP-OE to get our thermodynamic variables, but this has been a living code that has changed quite a bit. And because Houston is so moist, we had to make some different modifications to account for that. I don't know that those data were processed in the same way, and so I have not looked specifically into that.
Thanks. Any other questions from in the room? While people are pondering, so this is probably a little outside your wheelhouse, but there was an airborne campaign that took place in Houston. I don't remember if it was 2021 or 2022, but it was called Escape, and it was looking at sea breezes and convection. Have you thought about looking at any of that data, or would you consider comparisons?
Yeah, I would love to look into the data. So the Cubic campaign was a part of Tracer, and Escape was also very much a part of Tracer. So there are a lot of different data sources and different things to look at as a part of this. I have not looked into that data yet, but for some of the case study specific things I'd like to do, I know a couple of people who have worked on Escape, so I plan to connect with them to see whether we can share data and work together to look into more things. So,
Sure, that'd be interesting.
yeah.
Any other questions from the room? Tammy?
Thank you. Great talk, Michelle. Thanks for that. I'm going to ask you a question about the component that you said that you haven't put much effort into yet, and that is the the modeling of the convection initiation. What does your intuition tell you that is missing or is the most challenged for the model to accurately forecast the convection initiation along the sea breeze. It was really interesting that the sea breeze front was modeled in every member of that ensemble. So I'm curious what your thoughts are about the convection initiation not being represented well.
That's a great question. I think part of it has to do with just the differences in the mixing that takes place within the models. We have, different PBL schemes, and those handle mixing within the PBL differently. Also, while we see the temperature effects, I didn't have a chance to look into like the moisture, for instance, in some of the kinematic fields from the models. So I'm wondering if while we see the cooling from the sea breeze that the model does pick up on, if we're not advecting enough moisture, or that sea breeze front is just not strong enough to act as a lifting mechanism within the model to actually initiate and trigger that convection.
So to follow up on that, each of the different modeling algorithms use a different technique to get boundary layer depth. How do they compare to your method? And have you tried using your method on the on the model data at all?
Great question. I have not gotten there yet, so I do not know how to answer that yet. I am still very much in a literature review phase of PBL schemes used in modeling simulations. It's something I haven't, necessarily focused on specifically yet, so I'm trying to learn more about the parameterizations themselves so I can understand what may be happening there. I have not tried applying our algorithm to this, to the modeling simulations yet, but that's a really interesting idea. It'd be cool to see what that ends up looking like. But I'm not really sure what that looks like.
Great. We have one more question online from Young Jian. Do you have continuous surface flux measurements? Can you use these to assess effects of the urban heat island on the PBL heights? I'm also curious to learn how you identify sea breeze force convective initiation. Thanks.
Unfortunately, we do not have surface flux measurements. That is one of the downfalls of our current clamp systems. We don't have those kinds of measurements at our locations, unfortunately. In terms of the identifying the sea breeze force CI, I did this based off of radar observations. So I looked at NexRad radar. There was also a C-band scanning cloud radar as a part of the larger tracer campaign. So between those two radars, I just went through the entirety of the campaign and identified the sea breeze front. A lot of times you can see the front on radar, and then identified cases in which we have convective cells initiating right along that front.
Great, thanks. If there's no other pressing questions from the room, a reminder, Michelle will be here through the end of March, so you're welcome to stop by her office in FL1. Let's thank her again for that really interesting seminar.